Okay, I should be live. I need to change the picture. I don't have any control over the picture. That is all Anton. He just decides what he wants to put up, and I just live with it. So he thinks it's fun. So here's the horrifying reality of YouTube, and that is things that don't necessarily look good can induce clicks. And so you kind of have to live with this world where you're making stupid faces on your YouTube videos, and that encourages people to come and check out your content. And I don't make the rules, don't hate the player, hate the game. So yeah. So anyway, I should be live. I should have sound. Everything's good. Okay. Hey everyone, welcome to the question show. Now this is the live version, the sausage making revealed version of the question show. And so, of course, that means that, we're going to go at the pace of the questions coming in and me stopping and looking at the content. And so just like prepare yourself emotionally for not being the super slick version that you see edited after the fact. So some ground rules here. Go ahead and put any questions that you have for me into the YouTube chat, and the moderators and their robot pal will gather up those questions and they will throw them into a database that I can see and sort and review. So 3 rules. I think so far I still have 3 rules. Number 1, which is I try to give emphasis to the people who have never asked a question before. And so, we keep track of whose questions got into which question shows. And so if you've never had your question answered before, I like your chances. Now, that said, I am a journalist, not a scientist. And so if you're going to ask me a question that would require someone with a scientific background, I'm not your guy. I can distill and report on the scientific consensus, but I cannot provide any additional information or critical insights into stuff that is way beyond my pay grade. So I can tell you in general what scientists think. I cannot tell you what I think. Because I just don't think. And then the last thing is, we get a lot of questions, the same questions, week after week after week. And, I try to make sure that they get regular play, like a DJ in the question shows. But, if I skip the question, it just means probably we've answered this question a lot. But keep the questions short. Don't ask the same question many times. Wow, maybe there's 5 rules. Just ask the question once. The mods got it. It's in the database. I haven't answered it for a reason. So chill out. Now, this show is 2 hours long. And by sitting down and beginning to watch now, you are obligated. You have made an inexorable choice to watch the entire 2 hours. You're locked in, and there's no way out. So the first hour is the part that we edit down that turns into the question show that we post every week. And then the second hour, the secret hour, we call overtime. And that's where, depending on whether I'm feeling like I want to chew the scenery and answer questions slowly and with like lots of information, or maybe I want to go really quickly and machine gun through as many questions as I possibly can. Who knows? I don't know. So just keep in mind that you are here for 2 hours. You only do 95 minutes. 2 hours is the rule. And really, if you don't make it through the full 2 hours, we'll understand. Now, we're going to give you an intermission. So you can go to the bathroom, have a break. And so when we sort of reach the end and I start to do my sort of credits stuff, don't go anywhere because we're really only halfway through. All right. Let's get into it. Now, as always, I've got a bunch of prepared questions before. We'll do those first. And then we will get into your questions. And I don't know what it's going to be about. You make the show, not me. Live. recording reminder. Yes, I am recording. Here you go, Chad. Even Rose. Hey Fraser, when watching rocket launches, I'm fascinated by the crackling and popping sound of the engines. Does it sound like that in real life, and what causes this sound? So, yes, it sounds like that in real life. And in fact, the recording that you hear from NASA and SpaceX and so on doesn't do it justice because it sounds very high. Like you're hearing the rocket launch, you're hearing this kind of crackly poppy sound, and you definitely hear that. But there's another part of the rocket, and that is the sort of sound waves that are coming at you. And so when you see a rocket launch, and I've seen one, I watched the OSIRIS-REx mission launch, and I'm sure Chad has got some beautiful B-roll that he's going to play right now. We were several kilometers away from the launch site, and the rocket takes off, and it's silent, right? It's flash, you see it's silent as it's starting to go up. And then a few seconds later, you can see this sound wave moving across the bay as the sound is making its way towards you. And then as soon as it does, you hear all of the sound, that crackly poppy sound as the thing is taking off, but then you feel it. You feel sort of the pressure on your chest from the sound waves slamming into you one after the other. So what's causing that sound? So the way a rocket works is that it is expelling exhaust gases out of the back of the rocket. And thanks to Newton, we know that if you throw things out of the back of your rocket at high velocities, then you're going to get a kick in the opposite direction. And the only way to get the most efficient system is to fire those exhaust gases out at incredibly high speeds. So, for example, you're seeing the exhaust gases come out of the rocket between like 2,500 and 4,000 meters per second. It depends on the fuel, if it's a solid rocket motor, if it's a liquid rocket, whether it's methane, whether it's liquid oxygen and hydrogen. I mean, they all just kind of change. But just in general, these are going really fast. And so they are moving faster than the speed of sound when they are coming out. And they are immediately producing shock waves, sound, because they are going at supersonic speeds. And all of the different bits and pieces of gas are coming out, and they're interacting with their sound, and you're just getting this cacophony of cracks and popples. You're getting this cacophony of cracks and pops, and it is an unbelievable experience. And I've mentioned this in previous videos. Like if watching a rocket launch is on your life list of things to do, it's a relatively easy thing to knock off that list. That you can go out now to Cape Canaveral. It's a great place to take the kids. You can see all of history's great rockets. You can, and then you can stay at a place like, say, Cocoa Beach. There's hotels right there on the water. You get a nice hotel on the water, and SpaceX is launching rockets almost every week, sometimes within 24 hours of each other. And so if you just time things, or even just go for a week or two, or a week, you can watch a rocket go up. And the experience that you have from being at Cocoa Beach is roughly the same as the experience that you have closer up where we had it as journalists. So, if you can get to Orlando and then you rent a car and you drive out to Cocoa Beach and you stand on the beach when the rocket goes off, you will see it, you'll feel it, you'll experience it, and you'll understand just what an amazing accomplishment rocketry is. 3Dog 1963. You've said that space launches occur as close to the equatorial region as possible to get an assist from the spin of the Earth. So if the spin of the Earth were faster, launching heavier items would be easier. And conversely, if the spin were slower, it would be more difficult. At what point would the spin be so slow that we would be forever trapped on Earth? So your question is half right. In other words, yes, if the Earth was spinning more rapidly, then you would have an easier time launching from the equator. And this is just because the Earth is turning at a little over 1,000 kilometers per hour. And if you need to go into orbit around the Earth, you need to be going 28,000 kilometers per hour above the equator. And so you've already got 1,000, so you just have to make an additional 27,000 kilometers per hour to then be going in orbit around the Earth. But if the Earth was spinning faster, if it was going 2,000 kilometers per hour, then you'd only need to make up 26,000 kilometers per hour. And if it was going 10,000 kilometers per hour, then it would be even easier. But the problem is, at a certain point, the Earth would start to tear itself apart. And so really, sort of like the perfect spacefaring nation is the one that lives on a planet that is rotating just shy of completely tearing itself apart. And then you would have the easiest way to get into space. But the second half of your question was, like, what if you went the other way? And what if you slowed down? Well, no, there is no slowest speed. That if the planet was not rotating and you still wanted to go into orbit, then you would need to go 28,000. You have to pay the full fare of going into space. And we see versions of this all the time. Most of the time, you don't care where your rocket is going. You launch at the equator in the direction that the Earth is going. You just take advantage of that. And so if you've got a communication satellite or a weather satellite or a space station, that is the least expensive option. And so you take it. But if you are interested in your orbit, then sometimes you have to decline the discount. And so a good example is, say, a polar orbit. So when you think about the Earth and it's turning, and if you've launched from the equator and now you're going around the equator, and you can launch at a bit of an angle, so you're going a little bit above the equator, a little below the equator, then as the Earth is turning underneath you, you're going to see different parts of the Earth up to a maximum latitude above or below the equator. But there's going to be parts that you're just not going to be able to see. But if you launch on a polar orbit, that means that you're now launching towards, say, the North Pole or the South Pole. And you're now going, if the Earth is turning, you're going around the Earth like this. Now the Earth is going to turn underneath you, and so you're going to get a chance to see the entire planet. So that's a much better perspective for being able to view all of Earth. And you can sort of time things so that the same spots of the Earth appear on a regular interval as you're doing this polar orbit. But the price you pay is you have to pay the full ride. You don't get that 1,000 kilometer per hour discount. You've got to pay the full 28,000 kilometers per hour, which means either more rocket fuel or a lighter payload to be able to go into orbit. And you can even go in the opposite direction. You can go against the orbit of the Earth, but now you've got to pay an extra 1,000 to go in a retrograde orbit. So, yeah, that's how it works. I have globes. They're just not handy. I didn't think to bring a visual aid when I was going to answer that question. Yeah, retrograde. Chris Terrell, live active. Fraser, could you do a video on the setup you use to photograph or video auroras? I'm not the guy to give you detailed tutorials on how to photograph auroras. I've done my share of aurora photography, but I'm by no means a professional. And so, but I'll give you some quick tips. So we're at the point now in the modern technology where just your smartphone does a pretty good job of capturing an aurora. And a lot of the times when there is aurora activity and it should theoretically be visible in your area, and you go outside and you look to the north and you don't see anything, if you want to know if there is actually aurora activity, take a picture with your phone. And with the new iPhones, with the new Android phones, they're pretty good in low light and doing fairly long exposure photography, especially if you have a little tripod for it or you prop it up against something when you take the picture. It'll go for 10 seconds, 20 seconds, just try and do a long exposure image of the sky. And if you can't see the aurora with your eyes, but the phone may show it up. So I'm going to share a couple of pictures that I took on my recent trip to Iceland, and we could definitely see the auroras, but they were, like a hazy green cloud in the sky, and not with the purples and the pinks that you're seeing in this picture. So that's the first thing, is just use your phone. If you want to go to kind of like the next level, then you need to get like a DSLR camera. And then you need to be able to take you need to be able to take exposures of the sky. And the trick with auroras is that the length of the exposure that you're going to need to do to kind of take a picture of the aurora kind of depends on the strength and the level of the activity of the aurora. And people who have taken lots of pictures of auroras know exactly what I'm talking about, that there can be the kinds of auroras where it's just this sort of shimmering glow that's off on the horizon, and you'll do a 30-second exposure or a minute-long exposure, and what you get is kind of what you see, but better. But there are other auroras which are alive, that they are changing like writhing snakes in the sky, and that if you try to do a long exposure of 30 seconds or a minute, you just get this green mash that doesn't capture what it is that you were seeing. That in many cases, it's the shorter exposures that are the ones that are going to really kind of reveal the features and the details of what you saw. And so I'll share another video that I took, and in this case, I was doing very short exposures, and then I was turning them into the frames of a video, and that much better captures what we were seeing. But still, it's not quite what it's like to actually watch an aurora with your own eyes, or to watch a strong aurora with your own eyes. And I've never seen a video or image that captures it accurately, just because, like, I'm sure if like a really good camera that can handle really low light and it just shot at 60 frames a second and tried to just capture the aurora, maybe that'll get you there. But there is just something to be said for watching these things with your own eyes. And so if you're trying to set up to take photographs, be ready to put your camera down and just take it in with your eyeballs. Good luck. Oh, Chad's going to have so much B-roll he'll be able to work with. Okay, so those were all the prepared questions. So now let's get into your questions. Mark Scales, how big is the solar system? That's a great question. And it really sort of depends on what you define as the solar system. Where does the solar system begin and where does the solar system end? So let's talk about a couple of ways you could measure it. So you could say, okay, the planets are the end of the solar system. And that, with Neptune being the most distant planet, you're in a few billion kilometers away from the sun. But then you could say, well, no, like there's the Kuiper Belt and there's all of that stuff. So now you're sort of farther away. Let's switch to astronomical units, where each astronomical unit is the distance from the Earth to the sun. And so the Kuiper Belt is out in the sort of 60 to 100 astronomical unit range. And yet we know that the Voyager spacecraft have passed outside of the heliopause. And so when you think about the solar wind that's coming off of the sun, you've got these charged particles that are blasting out into space. But this is happening from every single star. And so there is this point where all of the collective solar winds from all of the stars in the Milky Way are bumping up against the solar wind that's coming from the sun. And because, it's closer to the sun, it's more concentrated, it has a stronger force. But eventually you reach this point where the interstellar cosmic wind, where the interstellar wind is stronger than the stellar wind, and that sort of defines an area, and that's called the heliosphere. And we know that the Voyager spacecraft recently exited the heliosphere, and it's a little farther than the Kuiper Belt. So that's another way. And so you'll hear these things like, oh, the Voyagers have left the solar system. Well, not exactly. They've left the heliosphere, but they're still in the gravitational dominance of the sun. And so sort of the next thing you can imagine as a way to describe the size of the solar system is the Oort cloud. The Oort cloud is this giant collection of icy objects that extend out for tens of thousands of astronomical units away from the sun. So you can measure that in terms of light years. Like they're It's believed that the Oort cloud could extend as far out as like 1 to 2 light years away from the sun. And when you think about how, if the same thing is happening at Alpha Centauri, extending out 1 to 2 light years away from Alpha Centauri, and Alpha Centauri and the sun are 4.5 light years away from each other, well, our Oort clouds are getting close to actually touching. So that is sort of a good way to describe the size of the solar system. I think when I really imagine the solar system, I think you got to include the Oort cloud. So now you're out 1 to 2 light years away from the sun. But, as we've talked about in previous videos, that you could be under the gravitational influence of the sun across the entire observable universe. You could be 13.8, well, you could be 46 billion light years away from the sun. You could see the sun in your telescope, and you would be experiencing the gravity from the sun. So are you still in the solar system? So you're just gonna have to decide where you think the solar system ends based on the stuff that I provided. John, your tag worked, by the way. Oops. Okay. TS Vlogs, what is the difference between time dilation when traveling at the speed of light versus when near a supermassive black hole? So I think it's really important to distinguish between I think it's important to distinguish how you put your question. And you said, what is the difference between time dilation when you are traveling at the speed of light versus when you're near a supermassive black hole? So the important thing with time dilation is acceleration, and not necessarily the velocity that you are going. And one of the big sort of insights that Einstein had, it was this idea of equivalence, that the experience of acceleration should be identical to the experience of being in a gravity field, in a gravity well. That if you're in a elevator and you can't tell whether you are accelerating, you're standing at the bottom of the elevator and you are accelerating up, or the elevator is hovering above some massive object and you are experiencing the acceleration, you can't tell the difference. And so then there is no difference. They are equivalent. That the time dilation that you experience when you are accelerating on your spacecraft, getting faster and closer to the speed of light, will be exactly the same as the acceleration that you will feel, the time dilation you will feel when you are close to a black hole, or like any kind of gravity well. It's just a matter of degree. So how much acceleration you get, whether you're in your space elevator or whether you're near a planet or a star or a black hole. Red Streak 1. How hard would it be to do a sample return from Europa, ignoring planetary protection concerns for the moment? It would be incredibly hard, but not impossible. So, let's think it through. So, in order to get to Europa in the first place, you would need to send a spacecraft. And the Europa Clipper just launched, so we can use that as an example. The Europa Clipper is the most massive interplanetary spacecraft that has ever been flown. It's 6,000 kilograms. It took a Falcon Heavy, which is one of the heaviest lift rockets that we have today. That wasn't even enough speed. Like the Falcon Heavy can't on its own get Europa Clipper to Jupiter. It'll have to do a flyby of Mars, and then a flyby of Earth, take a gravitational assist so it can be on the way. And then a lot of the mass of the Europa Clipper is propellant for it to, when it finally reaches Jupiter, to be able to put itself into the right orbit to be able to go around Europa. So let's say that that's your mission. You've sent this mission to Europa. Okay, now you've got to have a lander. You got to get down to the surface of Europa. So in addition to the orbiter that you sent to Europa, you're going to need several thousand kilograms of lander. And that's because the lander isn't just a lander. The lander also has an ascent module. In other words, the lander is going to be able to get down to the surface of Europa. And then when the samples have been delivered, they're going to be able to go back onto the ascent module, back up into orbit. And then you're going to need to be able to come home with them with some kind of return mission. So, above and beyond the orbiter, you're going to need to be able to fly back home to Earth. But the samples aren't sitting there on the surface of Europa. They're going to be underneath tens of kilometers of ice that you have to get through. Okay, so now there's a lot of people have proposed really interesting ideas on how you might be able to get down through that ice. You would have some kind of melt probe where you've got a decaying chunk of plutonium in the front of a thing that looks like a dart. And the thing aims down and the plutonium melts the water. Like the plutonium makes the front end of this probe very hot, and then it melts the ice in front of the probe, and the probe starts to sink down into the ice. And this has been tested out. Like people use this as a way to go under the ice in places like Greenland, like at meters per minute. It's actually quite an effective way to get under the ice. So you have a scaled up version of this. It might take you a couple of years to slowly melt down through the ice until you finally reach the water down below. And you have been spooling behind a wire that's been freezing into the inside the. You've been spooling a wire that is then frozen into the tube that you have melted behind you. And so now you deploy little robots that collect samples, and you're probably going to want samples from different places, not just the water right at the surface. Maybe you want to go all the way down and see if you can find black smokers or some kind of potential life. And then you bring those back to the probe. And here's the hard part, which is getting back up through the ice. And so to get down into the ice, all you had to do was use gravity, which would pull you down through the ice and melt behind you. But now you have to go against the gravity to climb up through tens of kilometers of ice. So maybe you've still got that plutonium that is in the bottom of your probe, and then you have to shift it up to the top so that now you're melting above you. And now you need some way, whether you can you can gain electricity from the decaying plutonium like the RTGs that we see on various spacecraft, so that you can start to climb up the inside of this tube that you have already dropped down. And I don't even know how that would be done. That is the hard part, is getting back up. And so then you're able to, but maybe you could float, as you liquefy the water and you maintain less pressure, you would float and stay at the top of the water. Maybe that would work. You remain buoyant and you would just keep floating up this column of water that you're creating. And then you would reach the top, and then you would pop open the top of your spacecraft. You would deliver the samples to the ascent module. The ascent module would take off from the surface of Europa. It would meet with the return capsule, and the return capsule would fly home to Earth. It would descend through the Earth's atmosphere, would land in the desert, probably Utah, and people would take it to a sealed facility, and they would open it up, and they would learn a tremendous amount about what is under the ice on Europa. That's cool. Let's make that happen. Church discography, guaranteed there are open cracks down to the water. Use those. Well, maybe. Oh, let's add this as well. But the other place in the solar system that would make this a lot easier is to go to Enceladus. Enceladus is one of the moons of Saturn. And in that case, you've got the water ice is actually spraying out. Or, in fact, at Enceladus, this water is spraying out into space. And in theory, if there are biological chemicals in that ice, you're going to be able to detect it. And you could detect it in situ. You could sort of smash your spacecraft into the ice and lick it, taste it, and that would tell you whether or not there's life there. But also you could pass through, collect samples, and you didn't even have to go down into a gravity well. And then you just fly back down to Earth and return those samples. So that's why we're going to see a sample return mission from Enceladus long before we see a sample return from Europa. Now I need to like bring people who have done this. Um, how heavy was Cassini? I don't know how heavy Cassini was. Cassini was originally supposed to launch. Oh, I'm thinking of Galileo. Yeah. Shard. Why are we worried about contamination from probes? Wouldn't any microbes die in the vacuum of space? Oh no. This is one of the horrifying discoveries that we have made is that human, no, and that is that Earth life is incredibly resilient to the most hostile environments we can possibly imagine. So there are experiments on the outside of the International Space Station. There are these boxes that have little sample capsules inside of them, and they will open up these doors so that the sample capsules are just exposed to the hard vacuum of space. And then various life forms from Earth, so cyanobacteria, archaea, mosses, lichens, of course, tardigrades, those hardy water bears, and other stuff, are seeds, things like that. They are exposed to the vacuum of space for years. So you're in the hot, cold as the space station is going around the Earth and going into and out of shadow. You've got the vacuum. You've got the intense radiation that you're experiencing above the Earth's atmosphere. And the complete lack of any kind of water. And then they bring the samples back down to Earth after a couple of years, and then they see how well the life forms did. And some are killed, but others, like cyanobacteria, tardigrades, they just wake up. You bring them back to Earth conditions. They wake up and get right back to what it is that they were doing as if they didn't even notice. And the cooler version of that experiment is they have also brought those life forms awake in Mars-like conditions, and where they do still have access to water, and found that, in fact, these microbes can handle living on Mars. And so when we attempt to sterilize a spacecraft, we can only do so good of a job. You can take a spacecraft, you can take every single part in the spacecraft, and you can bake it in an oven at hundreds of degrees, and then you can put together your spacecraft in a hermetically sealed room chamber that has no air coming into it, and then you can put it into your spacecraft, then you can put it into your rocket fairing, and you can launch it to space, and it will still have bacteria, Earth life, and some of that life is the kind of stuff that can handle the journey to Mars and thrive if it can find the right conditions on Mars. And so, we don't know if there are deposits of liquid water. There could be like patches of brine that are on the surface. And if life from Earth could find its way into some of those patches, it could conceivably grow. And if there's any indigenous life in those areas, then it would have to compete with Earth life. And it really feels like the Earth life, which has had like a lot more energy, a lot more evolution going on, it won't necessarily have the same adaptation. But we've seen here on Earth that you get invasive species that, the native species just get demolished by invasive species that are well adapted to that environment. So that's why you worry, is that we know that Earth life can survive and thrive in the most horrific conditions and recover. And so any spacecraft that we send out there, if they get to liquid water, then there's a really good chance that we're going to start infecting that water with Earth life. I baked my soil once and still got fruit flies. Yeah, yeah. Good rationale for not cleaning the house. It never really gets. Yeah, yeah. It's just by degree. Don't bother. Can't win. Mnokil. Are there plans to explore lava tubes on the moon or Mars? I tried to mass lab. Oh, I Mnokil. Mnokil. Are there plans to explore lava tubes on the moon or Mars? I toured a massive lava tube in Iceland today, and it had colonies of bacteria in absolute darkness. Trigger alert. I'm going to say the word lava a lot, and trigger alert. I'm going to say the word lava a lot with my Western Canadian accent, and I know it sounds wrong to your ears, but this is how we say the word here in Western Canada. Right. So yes, the various space agencies are really excited about the possibilities of exploring lava tubes on places like the moon or Mars. And there's a lot of really good reasons, really exciting reasons why you would want to go there. And so when you think about what happened, right, in the past, you've got some kind of volcanic event, you've got flows of lava that are coming down the side of some shield volcano, and it gets this crust that forms over top of it. And then the lava keeps going, and in many cases it will sort of completely vent out and leave the chamber that it has created underneath. And when you've got much lower gravity, the sizes of these chambers can be a lot larger. So while on Earth, maybe a lava tube is going to be tens of meters high, on the moon, it could be hundreds of meters, kilometers high. You could hide a whole city inside a lava tube on the moon. And so from just a protective place, they're incredibly useful, because if you set up inside a lava tube, then you're going to be protected from the radiation that's coming from space, that the temperature is going to be a lot more regulated. You're not going to be going through this hot and cold back and forth. And you also get this historical geologic record of the history of the moon inside the tube. And so there's like a lot of really good reasons. And you don't just have to sort of crack through the top of one of these tubes and spelunk down. There's a lot of places where you've got the exit point of that lava that I mentioned. And so there's going to be like a cave that you could just walk in and set up your base inside on the moon and on Mars. But we do see these lava tubes from space. You've got spacecraft that are orbiting around the moon and Mars. We can look down and we can see what they're called skylights, these collapsed tops. And very recently, the Lunar Reconnaissance Orbiter was able to do some mapping of the interior of one of these tubes and sort of get a sense of the true scale and shape of, and obviously it couldn't see as beyond sort of just peeking down one of these skylights. And then on Mars, it's even better, because you could have conditions where you might even have, say, briny water that is able to handle being in a low pressure environment, a very cold environment, when you're sort of just down in this lava tube. And then these are the places where you might find evidence of life on Mars, either past or present. And so they are like really much better, more safe, protective places to be able to explore. And then at the same time, though, they are scientifically fascinating, the most scientifically fascinating places that you could go to those worlds. And so they are huge priorities for every space agency. Pasta, Mazda, Llama. Have I chased you away yet? Buoy. do know the answer to this. All right. Okay. Jay Passer. Do we know how strong or weak the wind on Titan is? Yeah, we do. More or less. So when the Cassini-Huygens mission arrived at the Saturn system, the Huygens probe detached and flew down through the atmosphere of Titan. And when it was in the upper parts of the cloud tops, it was experiencing about 100, let me get this exactly right. When it was passing through the upper part of the atmosphere, it was experiencing winds of about 430 kilometers per hour. So that's really fast. But then as it got closer and closer to the surface, the wind speed slowed down and it wasn't moving very fast down at the bottom. But recently, astronomers have been looking at the seas on Titan. You know, we know that there are these oceans and seas of liquid methane on the surface of Titan closer to the poles. And they think that they were able to detect waves in these seas. And of course, you can't have waves without wind. And so there must be some kind of surface wind that is pushing this liquid methane around on the surface of Titan. And the waves are a couple of meters high. So theoretically, you could surf them, which is pretty cool. Now, we're going to find out really conclusive answers to these kinds of questions when NASA's Dragonfly mission takes off and gets to Titan 2035. Let me just get the right exact number. 2034. All right. Now we're going to get conclusive answers to this and many questions about Titan when NASA's Dragonfly mission flies to Titan. It's going to be launching in 2026, which is just 2 years from now, but it's not going to get there until 2034. But it will get there. So just, distract yourself with video games and books and movies and TV shows, and then you'll look up and wow, Dragonfly will be on Titan, and then the fun can begin. What else I wanted to say about that? There was something else I wanted to say about that. And if you're not familiar with the Dragonfly, this is a nuclear-powered quadcopter, a helicopter that's going to be flying on Titan. It's just crazy. Anyway, nuclear-powered helicopter on Titan. We've done whole episodes about it. I've done interviews with people behind the scenes. But anyway, Chad's going to hack all that out. But now that I talk about it, he's going to keep it all in because he's very meta this way. Ronald Big Money Anderson. I have a question. Don't they need legs to land on the moon or Mars? When will we see legs on Starship? Yeah, so with Starship landing on Earth, they're not putting legs on it, that it's going to get caught by Mechazilla in the same way that the Super Heavy booster was caught by Mechazilla. And that saves them a bunch of mass, and that means they can use less propellant or have larger payloads that they can send into orbit. But when they go to the moon, they will absolutely need some kind of landing legs at the bottom of Starship. But the good news is that on the moon, the gravity is 1/6 of what it is on Earth. And so the material strength that would be required to support the weight of Starship would be 1/6 of what it would be on Earth, and it would be 1/3 of what it would be on Earth if you were on Mars. So they will need landing legs, but they will be smaller than what they would be to try and support the weight on Earth. Now, that said, if we ever get to a point where there is significant infrastructure on Mars, you can imagine, or on the moon, you can imagine these spacecraft not having legs, that they arrive and there is a mechazilla waiting for them on the moon or Mars, and it captures them and puts them down gently. And this is we are building infrastructure for becoming a solar system spanning civilization. Subscriber stories artwork. Is this live? This is live. Oh, and that was your question. You can't wish for more wishes. Sorry, just looking for questions. Tyler Reeves, I've been enjoying your interviews with people chasing manufacturing in space, like the printed lunar solar cells. Any chance we get another episode or follow up on similar topics? I mean, yeah. I mean, I'm obsessed with the topic. And so whenever I see those kinds of questions, I reach out to try and do an interview. So hopefully the kinds of topics that I'm curious about and obsessed with are the ones that you're into as well. And so it will sort of sync up. Oh, that's a good point. Grail C, what do you think of the chances of Europa Clipper finding plumes and sampling them? So, I mean, Europa Clipper isn't, I'll do this as and Chad can just add this afterwards. Grail C, what do you think is the chance of Europa Clipper finding plumes and sampling them? So I mentioned in that question about Europa Clipper, I mentioned that question about getting a sample from Europa, that a better place to go to get a sample would be Enceladus, because we know that there are these geysers, plumes, blasting water ice out into space. But it's possible that there are these plumes at Europa as well. They have been theorized. There has been sort of some people thinking that they've found them and other people thinking that they haven't found them. But Europa Clipper will definitively tell us whether or not there are plumes and geysers at Europa, just like there is at Enceladus. Well, it won't be as extreme as Enceladus. Like, we know that. But if they are, Europa Clipper isn't equipped to detect the presence of life in the way that a dedicated mission that was designed to fly through the plumes of Enceladus or the plumes at Triton are. But it would still have a pretty great suite of instruments. And so you can imagine it flying through the plumes or close to the plumes and measuring the kinds of chemicals that it sees in the plumes. It would be looking for organic molecules. It'd be looking for the presence of things like hydrogen gas, which is food for bacteria. It'd be looking for the presence of carbon, nitrogen, other phosphorus, other chemicals that life might need. And, maybe you could even start to detect more complicated things like methane, ethane, ammonia, various things in those geysers. So no, like Europa Clipper just isn't equipped to detect the presence of life in plumes, but it could detect the plumes, and then from there, follow-on missions could be custom built to try to answer this question of, is there life under the ice on Europa? And that would be an easier mission than to try and find out if there's life at Enceladus. It's closer, it's easier to get to, but it may still be that flying through the plumes at Enceladus is our best chance. Like, if I had only one chance to search for life in the solar system, it would be to fly through the plumes of Enceladus, because we know there's hot water under the ice that's in contact with hot rock it contains all of the raw material that life requires. The question is just, is there life in it? David goes, will you and JMG ever have a Fermi Paradox rematch part 2 or possibly another topic? Well, I go on Jean-Michel Gaudier's channel every probably 6 months or so, but we just talk about all kinds of stuff. Yeah, I wonder how far away he is from me now that it's been a couple of years. I suspect he's drifted a lot closer to me in sort of my perspective of the Fermi Paradox, but it'd be interesting to sort of have a follow on. Yeah, I'll talk to him, see if he wants to have another conversation about it. Nunya Business. Any news on Starshot? So the Breakthrough Starshot, this was the project that was announced several years ago where people want to research using a laser sail to send a fleet of tiny spacecraft, microsatellites, to Alpha Centauri or Proxima Centauri. And this was quite exciting. It was founded. This was quite exciting. It's funded by a billionaire, so he's got deep pockets, and a lot of interesting projects rose up to sort of consider all of the various possibilities. But the reality of Project Starshot is that most of this is science fiction. Not Star Trek science fiction, not impossible science fiction, but that we don't have lasers powerful enough to be able to provide that kind of velocity to a spacecraft. We don't have the material science to build solar sails that are that small and that strong. We don't have the miniaturization of the technology to be able to provide that level of intelligence on the satellites. We don't have the ability to aim them and get them in the trajectory that we want them to go. So there is just an enormous amount of technological development that needs to go into this. And it is not like all of humanity is obsessed with this one goal. When you think about the three-body problem and the sort of single-minded obsession of the Trisolarans, when you think about Project Hail Mary, and you think about how all of the world's resources were channeled to this one task in Project Hail Mary, we don't have that. We have a billionaire who is funding a bunch of scientists and engineers to work on some ideas, but we are just so far away from the technological readiness to start to consider this. But, we discuss in bits and pieces here on the channel, and I do tons of interviews with people because I'm obsessed with this topic as well. We do interviews with people who are thinking about, what would be the best way to communicate with all of those probes, or what would be the best place to put a laser so if we wanted to fire it and not cause damage to Earth, where should we put it? What are some possible materials for the solar sails that would make a lot of sense to be able to both provide the strength when you're getting hit by the laser and not just melt, but also provide the acceleration that's required to get the spacecraft up to 20% the speed of light. So, I want you to manage your expectations that we are likely many decades away from practical prototypes of this kind of technology actually being tested. And we're going to see it tested here in the solar system. You're going to see tons and tons of lasers. Like NASA has launched a solar sail and is now starting to operate it. And that's not like a laser sail. It's not miniaturized. It's literally just, can we make a solar sail work? So no one has tested laser sails in space yet. So there's just a huge stack of technology that needs to be done. So, I will bring you every single iteration of this technology as people develop it and work on it and obsess about it. And, you will watch the entire history of humanity's exploration of interstellar space in real time here on my channel, but it's going to be too slow for what you want. And I know that. I've been doing this job for 25 years. Did you think that 25 years ago I would be still waiting many years for people to go to Mars? No, it was going to happen. I read the case for Mars. It was going to happen within a couple of years. And yet here I am, old, gray, ready for retirement. And it still hasn't happened yet. So I'm not going to retire. Don't worry about it. So no news. When there is news, I will bring you all the news and the interviews. Okay. So that is the end of the main portion of the question show. But as I mentioned, you are contractually obligated to stick around for the entire show, the next hour. I don't make the rules. It's just by watching it, this is what you agreed to. So we're going to do some stupid administration first. So go ahead, go to the bathroom, grab some food, remind your loved ones that you still exist and you love them, and then come back in 5 minutes and we will move on to overtime where we will shake things up somehow. Kimber, oh, my beer is low. Now I can top up. Yeah, that's dangerous. Refill the beer. Why do rockets make crackly poppy sounds? Would a faster spinning planet be easier to launch from? And what's the best way to photograph auroras? Okay. Why do rockets make that crackling and popping sound? If the Earth spun faster, would it be easier to launch rockets? And what's the best way to photograph auroras? All this and more in this week's question show. Okay. Welcome to the question show. Your questions, my answers, as always, wherever you are across my channel. If a question pops in your brain, just go to the YouTube comments, write it down. I will gather a bunch of them up and I will answer them here. All right, let's get into the questions. I'm sure you noticed the Star Trek planet name that appeared above my shoulder. Oh, not Star Trek. I'm sure you noticed the Stargate planet name that appeared above my shoulder, and this is a way for you to vote, for you to tell us what you thought was the best question of the week, the best answer of the week, the best combo, whatever struck your fancy. So the winner from last week was S. Morrow. Could we ever work out exactly how many years old the universe is? So thank you everyone who voted. Now we're going to put a different Stargate planet name up above my shoulder with each question, and then we're going to count up all of the votes, and we will celebrate that next week. So we'll put the list in the We'll put the list down in the show notes down below. And so just wait, watch all of the questions, evaluate very carefully, and then tell us what you thought was the best question. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who has already subscribed, and welcome to our recent newcomers: John Deward, Paul Carr, Yvonne, Peter Oberle, Stan Spanish, Jamjari Weol, Tricor, Brandon Lee, Daniel, Kevin Sheridan, Stephen Gearhart, and Daryl Stewart. Join the club at Universe Today. Join the club at patreon.com/Universe Today. All right, those were all the questions that we got this week. Thank everyone who put your questions into the YouTube comments, and thank you everyone who joined me for the live show that we record every Monday at 5 p.m. Pacific time here on YouTube. Of course, we are going to be mixing things up shortly. We're going to be having some episodes be for people in North America, some episodes for people who live in Europe, and some episodes for people who live in Asia and Australia. So stay tuned. The actual live event times are going to change slightly. Now, I'm going to talk about a really exciting development that we're going to be bringing back. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew M. Gross, Barry Lake Roofing, David Gilton, and David Matz, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Rohrbach, ScienceWorldRecord.org, Spiderswap.io, Stephen Filer Munley, and Vlad Shiplin, who support us at the Master of the Universe level. And all of our patrons. All your support means the universe to us. So one of the questions that people have been asking me many times is, when are the virtual star parties going to come back? And my answer has been that they're probably not going to come back. And that is because it is just always so complicated and difficult to be able to wrangle astronomers, to be able to coordinate people's times. You have bad weather and gear and all of that. And it just, burned out anybody who volunteered to try and coordinate this activity. Well, we've got a new solution, which is our good friends at Starfront are going to provide us with a telescope and a mount. And this is a server co-location. This is a telescope co-location where you've got tons of telescopes in one of the most pristine dark sky places in the world. And they're supplying a really powerful telescope. It's a Celestron Origins telescope. And if you've never heard of it, this is sort of like a really fancy smart scope that is able to take really good pictures of the night sky very quickly. And we've been doing a bunch of tests. I'm going to show you a couple of the pictures that I've been doing. And keep in mind, these are just test shots, the kinds of things that I was capturing in 30 seconds, 90 seconds, the kinds of stuff that we could show live, the comet, the moon, various nebulae, galaxies, things like that. And so with almost always having clear skies, access to a powerful telescope that we're going to be able to use, we now have a really firm foundation for being able to bring the virtual star parties back. And then we can layer on top of that guests and other telescopes and friends and celebrities and people who want to experience the night sky. And so thanks in advance to Starfront for being able to help make this finally a reality. And I am so excited about what we're going to be able to do from here on out. So stay tuned for upcoming virtual star parties. And it might even be by the time you watch this, we have already done one. All right. Thanks, everyone, and we will see you next week. Okay. Did you just ask when the virtual star party is going to come back? This is 260? No. 62, 3, 4, 5, 6. I don't even know what episode this is. 68. We're in the 270s. What? All right, 271. Okay. Okay. Let's start the next part. Hello, patrons. You are listening to the overtime questions for Monday, October 21st, 2024. All right, let's get into the additional questions. For those of you who are watching this live, yeah, we post the audio for the overtime for the patrons. Just another good reason to become a patron. All right, let's get into the overtime questions. It's all right. Just looking through all the questions. All right, let's just start at the back. Okay. Full Metal Celestron. 2001. Space Celestron. If I can share. If you go to my YouTube, there's some picture. Let me see if I can share the picture. Where do I have a copy of it? I mean, people will see them in the edited version, but here we go. To see if this works. So that is the kind of thing that we could do live in 30 seconds. And this thing is so fast. When are you moving to Alberta? Never. Oh my God. Why would I go to Alberta? It is so cold there. Oh. Paul Hellinga, I would love to see you interview Dr. Kipping of Cool Worlds. Like, again? I think he's one of the people I've interviewed the most. Definitely do a search for Kipping on my channel. Neil von Hultum, when are they going to finish building the insanely large telescope? Yeah, after they finish the inevitable large telescope. So a bunch of people are asking about this breakthrough listen candidate. I haven't been following the news. So, I mean, my initial instinct is to be skeptical. I think I saw Sabina had done a video on this, so we've reported on the past. I'll definitely be looking into it. It just hasn't crossed my desk, so it didn't come through a more standard press release, journal article, that kind of thing. So, yeah, a whole bunch of people are asking this question. I have no insights to give you. Louis Alexander Parent, should common space-related conspiracy theories be better or at all taught in school? I feel science teachers would have the proper fact-based influence with students to fight all the nonsense. You can't fight nonsense by trying to sort of, okay. So when my kids were young, we used to play a game called Snopes. And what we would do is I would go to an entry on Snopes, which is this really cool website that keeps track of myths and conspiracy theories and things like that. And I would read out the thing, right? And then the kids would have to figure out whether or not this was real or not, whether it was true or was fake. And they loved it. And it was great because then we would do some research, and when something was actually true, it was sort of like a really interesting conversation. And so I don't think that you can teach children or adults to specifically believe or be specifically aware that there are various conspiracies, because if something doesn't sort of pattern match the exact conspiracy that they have been trained for, then it will slip through and it will infect their brain. But the thing that you need to do, and this is what Carl Sagan was always a big fan of, was to build people's baloney detection kits that you have to build a scientific mindset perspective on how you evaluate the kinds of truth claims that are being made at you, right? And so when we sort of read through health news in the newspaper, when we think about when people are mentioning conspiracy theories on the internet, things like that, that you can approach this with a scientific mindset, a skeptical mindset when you think about these things. And in many cases, a lot of that stuff just doesn't pass the sniff test. And so you could just ignore it immediately. And so, no, I think we don't teach specific conspiracy theories. We teach rational thought. We teach ways of evaluating statistics and evidence and like how people come to rational conclusions. That's the kind of thing that then can stick with them for life. And so now, I will often talk to my son and he'll be like, "Oh, I heard this thing. And I was, it's obviously total bullshit." And I'm like, yeah, good one. Right. You're right. Because he just has that skeptical mindset. And I do think that kids these days are very familiar with the idea. Like, I'm sure a bunch of you right now are watching this. Like, I'm sure some of you are young right now, and you are very kind of just default skeptical about when you see something. You're like, it's probably AI. Oh, that probably didn't happen. Oh, that's probably disinformation. Oh, that's probably, some ridiculous claim that's being made by somebody and it's not true. And that it's in fact older generations who grew up in this media world where Walter Cronkite was telling you that something was the way it was, and you just believed it because he was, the top a pillar of journalists, of hardworking journalists that were out there attempting to determine whether or not things were true or not. And so there was this base level of trust and expertise and so on. And that was good because people could just agree that reality was reality, but it was bad because you delegated your skepticism, you delegated your truth seeking to other people. And now we're all having to evaluate things in real time. And so I hope, like when someone goes, "Oh, look at this cool picture, look at this sad picture," I'm like, before I even look at it, I'm like, it's probably AI, but I'll take a look. And then I'll be like, okay, this looks real, like they've got the right number of fingers. Now, how can I figure out what is a source that is related to this picture or news that I can trust? Like, is NASA telling me that they have discovered a signal coming from Proxima Centauri, or is it showing up in videos on YouTube? And so yeah, I think the current generation, sadly, the young people today they live in a world where you kind of can't trust anything by default, and that you've got to figure out whether or not things are true or not before you take action. You don't want to get sucked in because somebody was, fooled you. And so I think that this next generation, the kids are all right. They are going to be very resilient and able to resist people's attempts to hack their brains, because they're on guard for this all the time. And that's like the downside, is that you have to be on guard for this all the time. You can't just live in a trusting society. You've got to be skeptical and suspicious of when people are sending you things and trying to tell you things. So that's my opinion. But the kids that are there, the people who are, say, under 20, tell me if that does that match your perspective? Do you feel like you have to spend a lot of your time just not believing things that people are trying to show you? Be interesting. Church discography. Do you still plan to mess with the QA schedule? Yeah. So we're going to do 2 shows a month at this time slot, 1 show a month for Europe and 1 show a month for Asia and Australia. There you go. Sanctuary cryptid all the time. Joshua agree. So yeah, so you guys are gonna be fine. You're not gonna get fooled. And other people will, but they will learn the terrible hard lesson, and they will learn to become more skeptical over time. And like every time humanity faces a new technology, we are caught flat-footed, and there is enormous upheaval and change. And you think about when the printing press was introduced, it led to wars, religious wars. And we're not having religious wars. We are merely having people try to lie towards each other to try to distort reality. So, and we will learn to live in a world where trust and truth is a rare and rare commodity, and something that needs to be protected and preserved, and you seek it out. And so that's like one of the things, people are always say, oh, are you worried about AI taking your job? And I actually think that in a world of slop, AI slop that is coming for us, the tidal waves of AI slop that are making their way towards everyone, that people are going to go like, okay, fine. So where's a place that I can go that I can see space news reported by actual human journalists who are attempting to tell the truth? Oh, Universe Today, that's the place. So I actually think we'll do okay. What's Fraser going to do in a 5 Monday month? Yeah. So stop asking me about BLC1. I have no opinion right now. Russell Breyer, how restricted is JWST field of view because of the sun shield? So the sun, when you think about JWST, it has this tennis court sized sun shield, and the telescope is on the other side of the sun shield. And so the sun shield is blocking the view to the sun and the earth and the moon. And so for when JWST is observing, it can only see half of the sky, but it actually can see even less than that, because the telescope itself can only, and I forget the exact number, it's like it can only go down 45 degrees. If you sort of imagine, here's the sun shield, and the telescope can kind of go like this, and then it can kind of go like that, right? And so it can't look down, it can't look straight up, it can only look sort of like at this angle. But that's for so that's half of the year. 6 months later, now the sun shield is in the completely opposite direction, and now the telescope is able to look at the other half of the sky. But even more so, the telescope is turned so that it's looking downstream of its orbital direction. So, we learned that there are more micrometeorite impacts hitting it, and in some cases there are some larger ones than people are expecting. And so they've changed the way they observe with James Webb so that it is now, so if you imagine it's moving in orbit this way, it's going to turn back and look downstream. And so, turn the sun shield on the side, and it can go sort of looking around as it's going around the sun. I know my hands don't make great sun shields and James Webb telescopes. But, and so like over the course of an entire year, they can have it look at any object that they want. They just can't look at all of the objects at the same time, depending on its orientation. So it's restricted at any one time. If they're like, quick, we have to look at this object and it's near the sun, James Webb cannot participate. Oh, this is a good question. Mikhail Billman, how do we preserve history? SSDs don't last forever. Quantum computing? This is a question, like, that haunts me, which is, how do we protect history? So in the olden days, Byzantium, or the Byzantine Empire, who was it? The Sumerians, right? So the Sumerians would use clay tablets, and they would store records about their existence. And then you had people writing on text in papyrus, and then you had the printed page in the book, and you had all of these historical artifacts that were a history of human society. But since the 2000s, we have put everything that we do onto the internet, and there is no record of what we do that isn't under electrons. And so if for some reason I decide that I don't want to run Universe Today anymore, and I don't want to, nobody wants to step up and keep running the website, then its server bills will go unpaid and the website will go offline. And of course, we've seen that countless times, that web pages go offline. And so 30,000 news stories about space, 25 years of space exploration, would just no longer be accessible. Now, there would be mirrors, and there, because of my Creative Commons 4.0 license, people would have been making plenty of copies of what we've done, but you're going to lose that direct connection to the history that we reported. And we saw with archive.org, it went offline. Like the Wayback Machine, the history of the internet that is being stored, like they are recording this history of the internet every couple of days on every single website that is relevant. They were offline for a little while. They're back in read-only mode right now while I'm talking about this. But there was, people are trying to sue them, and they may sue them out of existence, that the very history of the internet might just disappear. And so it's entirely feasible, possible to believe that 20 years from now, 50 years from now, 100 years from now, we will have no history, right? We will have no written history, that every article that was ever written, every story that was done, every podcast that was recorded, every video that was recorded, that was stored on a server, on a, somewhere, people stopped paying the server bills and the data was destroyed, the hard drive was overwritten, the material was gone, and we will be living in the moment, and that we will have no just permanent archive of what came before. Now there's a couple of sort of interesting projects. Like I know that in Europe, I think in England, I know Tom Scott did a video about this, that there's a giant library where they print off websites and keep them in this giant archive. But yeah, we are like you, or the world, or in the future of humanity is depending on me to pay my server bills, to maintain what is one of the most comprehensive archives of the history of space exploration in the early 21st century, right? We have 30,000 articles on Universe Today. I pay $1,000 a month to maintain that server. And if at some point, $1,000 a month, at some point I retire, nobody wants to take Universe Today off my hands, I can no longer pay the expenses, it'll just vanish. So it's a problem. It's a big problem. And it sort of occurred to me like 25 years ago. I actually wrote a letter to politicians in Canada. Like I think our like chief librarian, I forget what it was, like our information. Anyway, I wrote a letter, and I printed off and I signed it with this exact concern. And I sent it to the government and said, I'm really concerned about what's going to happen. And nobody got back to me, and nobody, yeah. So anyway, yeah. So that is the future. That's the future. There will be no past. It sounds like a science fiction story. Yeah, it's such a great question. Thank you. you're all want to talk about BLC1. I don't know anything about BLC1. Oh, Mr. Man, I'm late, but have we discussed the death of the Kerbal Space Program forums? There's an example, right? There once was a place where you could go and you could discuss the Kerbal Space Program and get solutions and ideas and suggestions from other players. And now that just doesn't exist anymore. Dougal, have you ever spoken with Angry Astronaut and or Ellie in Space? I have not. No reason. There's just a lot of people. And I'm happy with, like, I feel like Scott and Marcus have perspectives, like very similar perspectives, but sort of different overlapping knowledge, but also stuff that they really specialize in. And so I feel like I like to bring them on for these Starship recaps. Pepsi Cola, your camera quality is impeccable. Yeah, I'm using a Sony FX3 camera, and I'm using it as a fancy webcam. But I got it so that I could take it on the road and record more documentary style stuff. Although now that I'm looking at it, it's got really nice spider webs on it, so it hasn't moved from this spot for the better part of 6 months. But I like this camera for a couple of reasons. It doesn't overheat. So I have my old webcam, which is right here. So this was my old webcam, which was the Sony A7C, and it's a great camera, but it would overheat because it's not a video camera. It's a still camera that can do great video, but you leave it running for 60 minutes. And I had a bunch of times where it just shut off. It just turned off. And we're like, well, great. So now you don't have a camera. So there was only so long that I could keep using that camera as my webcam. And with the FX3, it's a proper video camera. It has rock solid, focus, which other cameras that I've had just don't have good focus, and this thing just has amazing focus. And then it'll do 60 frames a second at 4K. And so all of the videos that we produce are sort of future proofed. We record everything at 60 frames a second at 4K, and then that allows us to sort of maintain the consistency into the future. Neil Von Holtum, how hard would it be to use our sun as a magnifying glass? Not hard. Have you ever used the sun as a magnifying glass? You could just use a magnifying glass to concentrate the energy of the sun. But yeah, you're talking about the solar gravitational lens. How hard would it be? All you would have to do is fly a spacecraft out to about 500 astronomical units away from the sun, which is 10 times farther than any spacecraft has ever been sent. And then you would have to, how far are the Voyagers? 100 AU? Hold on. 165. Okay, so it would be, say, 4 times farther than any spacecraft has ever gone. And you'd want to do it in a reasonable amount of time. You wouldn't want to take 50 years if it takes you 50 years to get to 150 AU, you'd need 200 years to get out to 600 AU. So you need to go fast. And so that's the tricky part about getting to the solar gravitational lens, is that you've got to figure out a way to go really, really fast. And so, I've got 2 interviews with Dr. Slava Turyshev. He's the person who came up with the idea of the solar gravitational lens. So definitely, if you're interested in this topic, do a search on my channel for Slava Turyshev. And actually, I'll give you the link. And you can watch the interview. And that will tell you how hard it is. Spoiler alert, hard. There you go. Okay, so that's the interview with Slava Turyshev. He's a treasure. He's one of my favorite people to interview. He's so much fun. Dougal, will Juno still be operational when Clipper and Juice arrives? Hopefully. I mean, there's no reason, like, Juno is solar powered, so it's still operating. They keep doing extensions on its mission, and in recently they've started sending Juno on much more dangerous trajectories. So now they've had it been doing flybys of Io, which is you have to get very close to the radiation environment around Jupiter. So they've moved into the mode of flying Juno, but hopefully it'll still be operational when Clipper and Juice get there. Arjone had a good question. Arjone, when we visit other planets, will we find everyone's ancient civilizations? Um, yeah, it's crazy to think like the distance between stars is so vast, especially when you think about the amount of time that it would take to actually travel from star system to star system, that that even when we see a civilization, we think about like the history of humanity. Um, a civilization that's 100 light years away from us is seeing us 100 years ago. They're, we've just started to develop flying machines, the internal combustion engine, like what humanity looked like in 1924 is dramatically different than what it looks like in 2024. But that's nothing compared to the amount of time that it would take to actually cross the gulf between stars, to fly from one star system to another star system. That we could actually make the journey at the very fastest. If we go 20% the speed of light, 10% the speed of light, we're turning a 100 light years of distance into 1,000 years of travel. Like we really can only go to the closest star systems, to Proxima Centauri, Barnard Star, things that are just a few light years away from us, to actually try, it could take us 50 years to get to Proxima Centauri, that you could be a grad student when you begin on your mission and you're ready for retirement when your mission arrives at Proxima Centauri. And so wherever we go, wherever we see, whatever we want to explore, we are looking in the past. And I think that's the biggest problem that science fiction has filled our head with, right? Is that at Star Trek, Star Wars, everything's in real time, that you get in your spaceship and you're communicating with other people halfway across the galaxy, and you go to warp speed and you arrive at your destination, and it's just like hopping in a ship and going from one island to another island. But it's nothing like that. And yet now that has primed us. It's changed our expectations that, space flight should be like that, and that anything less than a warp drive is unacceptable. And yet it might be that we can never move faster than the speed of light. You think about the implications. If faster than light travel is possible, then we should see alien civilizations moving all over the place. They should be arriving all of the time. And so the fact that we don't see, it's like another paradox, right? The fact that we don't see warp drive aliens here means that either we're alone in the universe, and so we will be the first and only civilization to develop warp drives, or warp drives are impossible. Because imagine, if warp drives are possible, then you could have then the observable universe is no longer the limit. You could go 100 trillion light years to travel faster than the speed of light. And so not only do we not see evidence of aliens in the observable universe, we don't see evidence of aliens who have been flying in warp drives from beyond the observable universe. And so that just is more. So either we're alone or warp drives are impossible. But you can't have both. You can't be in a populated universe where warp drives are possible. It's the same thing with time travel, right? That that if there's a future and people will develop time travel in the future, then we should be inundated with time travelers because there's like an infinite amount of time in the future. Adventures of Carl. A couple of my coworkers have been asking, what is a good telescope under $200? What do you recommend? I if you've only got $200 to spend, I do not recommend a telescope. I recommend a pair of binoculars. So a couple of people have been mentioning this. The Celestron 15 by 70 binoculars. They're astronomical binoculars. They're monsters. Very big binoculars. And so the 15 is the magnification. The 70 is the size of the lenses, 70 millimeters across on the lenses. They're two giant lenses. So those are the ones that I recommend for people, and they cost between $50 and $100 depending on when they're on sale. And they are your just go-to telescope, like, or gear. Like, I use the binoculars daily. Birds in the day, stars at night. And with a pair of binoculars, you could see that comet, A3. You can see Saturn, you can see Jupiter, you can see the moon, you can see deep sky objects, globular clusters, you can see Andromeda Galaxy, you can see open star clusters. Like, there's a lot of stuff that you can see with a good pair of binoculars. And so I would rather get, like, if you only got $200, I would get the best binoculars that I could afford, and not try to get a telescope. The sort of minimum telescope to get is probably a 6-inch Dobsonian. I mean, I don't know if people make a 4-inch Dobsonian. That's still pretty good. But a 6-inch Dobsonian would be a good way to go. You could also get like a Celestron first scope. They're okay, but they're like small. I think they're 130 millimeter, and made of cardboard, but they're like $100. So what you don't want, and people don't really sell these anymore, is the department store refractor, the sort of the long telescope on the really janky tripod that just falls apart when you try to use it. So, it's been more like, I mean, you could get a used Dobsonian for $200, or maybe like a used telescope from someone else for $200. But if you want to get like a good entry telescope, you're looking at about $350 for a Dobsonian. And that's what I would get. But can you see Uranus? You can see Uranus with, you can't, yes. If you know where to look, you can see Uranus with a pair of binoculars. And if you, it'll just look like a little blue dot. But if you know what you're looking at, you'll totally recognize it. It's funny. Uranus is just within the ability for the human eye to be able to see it. And so it's possible that people have actually seen it and discovered it in the past. But nobody has there's no written record of anybody saying, I think I've seen a planet. It wasn't until telescopes were invented that people actually started to do that. Creative Wizard, could you briefly describe what the process was with SpaceX Mechzilla? Based on seeing the videos and reading it all, I could see was explosions. Well, all right. I'm not sure sort of where we want to sort of begin this conversation. So originally, when SpaceX was developing their reusable rocketry with the Falcon 9, for example, these things land propulsively on a barge out in the sea, and then they bring them back. And as SpaceX was developing the fully reusable two-stage rocket concept with the Super Heavy booster and the Starship, they realized that the amount of payload that they're going to be able to actually carry to space is relatively small for the size of the rocket. Now, the benefit is that the whole thing is reusable. You don't throw out your rocket every time the way they do with other rockets. But the only way to be able to achieve that full reusability was to shave off all of the weight from the rocket. And so one of the ways of saving a lot of weight is to not have any landing gear on your rocket. And so in the idea, and I think this is genius, right? The idea was, well, let's catch the rocket so it doesn't need to have landing gear. And instead, it just has some hard points on sort of up near the top that it can rest on. And so the booster, when it launches and you get the separation of the Starship, and then the booster flips around and then it fires its engines and it flies back to the launch site and then decelerates and then sort of brings itself close to the tower. And then at the last minute, when it knew that it was able to make it without exploding, it sort of shifted sideways. And then on the launch tower, the Mechazilla, it's got these big, they call them chopsticks, but these big arms that close in, and those hard points, they're like little knobs on the sides of the rocket, just touch down on the tops of these chopsticks. And then the chopsticks have a, they're able to kind of catch it, and they have shock absorbers so that they sort of dip down when the rocket, it sort of rests on top of it. And they were able to cut off tons of weight. I mean that like metric tons of weight off of the dry mass of the super heavy booster by not having any kind of landing system on it beyond those little knobs that it gets caught with the chopsticks. So it's an incredible idea, and it is by far the most exciting part of that entire Flight 5 was that they actually pulled this off and caught it. And the risks are huge, right? Because this thing is a bomb. And so imagine if it's a little off, they don't quite make the catch, and then the thing crashes into the launch gantry and explodes. And now you've not only lost the rocket, but you've lost the entire launch tower. So to go this route is scary. I can just imagine the meeting. I mean, I wish I knew who actually came up with that idea and said, look, what if we don't, we need a way to shave off the landing gear weight of this rocket. And someone was like, what if we don't have any landing gear? Wait, what? Yeah, it must have been incredible. Busy Billy B33, will you do a collab when New Glenn launches and attempts a first time landing on a barge? Yeah, I think so. I think we'll pull off we'll probably try and do a collaboration. Maybe I'll find some, different people for the New Glenn people, but we'll see. But yeah, I think that's a good idea. I really enjoy doing those kinds of collaborative conversations, and I'm always looking for excuses to bring together people, especially people that have a lot less of an audience, so I can try and showcase them and help them get more followers. Like, I think that's the responsibility of the people who have more followers on YouTube, is to drive eyeballs and awareness and audience to the people who have less. I should be shouting out people with smaller audiences again. Yeah. Joe Jr. Why doesn't the scientific community ever refer to our moon and the sun by their proper names, Luna and Sol? Because they're not really the official proper names. They're just the word sun and moon in another language. So, I mean, is that really should we call Mars Aries? Is that the official name of Mars? Is Aries? It's just, you're saying the same word, you're just saying it in a different language. So Terra, we call Earth Terra, which is a different language. Sure, fine. We could say, we could call the, so in Chinese, the moon is Yue. So why don't we just call it Yue, right? Which, those of you who've watched Avatar, The Last Airbender, that's going to blow your mind when you know that the name for the moon is Yue. So it's, that's not really the real name is moon, translated into every language. And the moon. So the moon does have a name, and it is the moon. Capital T-H-E, capital M-O-O-N. The moon. the earth and the sun, and also the universe. THE, capital THE, capital U, NIVRESE, the universe. So, we have a style guide at Universe Today when any new writers join us. And in the style guide is, here's how you reference the moon, which is that you have to capitalize moon, because that distinguishes it from just regular other moons. And same thing with the sun, and same thing with the universe. And so that's how you know that it's the real name of the thing. And that just drives people crazy, that the name of the moon is the moon, when you're just translating into Spanish or Rome, or or into Latin or whatever. It's still the same word. Kirk Wagner, or faster than light flight requires tech that we don't know how to detect yet. So, I mean, I think the point is, like, we may not be able to detect the flight that, the way that faster than light aliens are using to explore space. But the point is that they're going to be going to destinations, and one of those destinations is going to be the Earth. And if there's an infinite universe and people are able to go faster than the speed of light, then there should be an infinite number of aliens who are traveling faster than the speed of light to infinite destinations. And many of those are going to be Earth an infinite number of times. So, we may not be able to observe the aliens flying past, but we've definitely observed the aliens arriving on Earth with their giant spaceships. If we can't detect them, even though they're arriving here on Earth, then have they really come here? People always say that. Well, like, what if we can't, like, detect the aliens with anything that we can't detect them scientifically, we can't measure them, we can't, they're like in another dimension, man. I'm like, well, then they're not here. It's the equivalent of them being not here, right? If we can't detect them, then they don't exist. Carl Sagan had this sort of great example in the book Demon Haunted World, which was one of the most influential books that I've ever read. And he sort of talks about how you have a friend who tells you they've got a dragon in their garage. You're like, whoa, a dragon in your garage. Can I see it? And he goes, whoa. It's an invisible dragon. You can't see it. Oh, that's no problem. It's got to be, like, physically there so I can feel it, right? It's like, well, no. It's an insubstantial dragon. It's invisible and you can't feel it, but it is there. Okay, no problem. I can use an infrared sensor to be able to detect the warmth. No. It doesn't give off any heat. Okay, no problem. I can detect neutrinos. I can, and it doesn't do any of those things. You're like, I don't think you have a dragon in your garage. So, you got to see man with more dudeness. You always have to sort of draw that line between a complete stoner and a philosopher. But that's what I'm going for. Dark matter, dark energy? No. So imagine, right? Someone says, I have a dragon in my garage. And you're like, oh, okay, sure you do. Yeah, he's like, you're like, can I see it? And you're like, no, it's invisible. Okay, no problem. But I should be able to detect its presence, the weight of the dragon moving around on the floor. And he's like, oh yeah, come on and check this out. And you go and you look at the garage, you could see giant footprints moving around inside the garage as the gravity is pulling the dragon down. It is crunching the concrete as it's moving around. That's dark matter, right? So yeah, we can't see it, but boy, can we measure its gravity, because it is 10 times as much as regular matter. So to go like, oh, dark matter is like invisible, man. Yeah, not gravitationally. Joshua, have they come up with a moon time zone yet? They're almost there. So the European Space Agency and other agencies are meeting and have been working on the specific time zones for the moon. And there's like a couple of issues. Like one is that the moon moves through the sky, and so it doesn't match any specific time zone on Earth. It changes as it moves. And then the other thing, and this is sort of really kind of sort of harder to catch, is that the mass of the moon is lower than the mass of the Earth. And so time moves differently when you are on the surface of the moon than when you are on the surface of the Earth. And that's not a big deal, but for atomic clocks and for global positioning systems, it absolutely matters. And so they need to figure out a way to deal with the drift of time between observers on the Earth and observers on the moon. Sean Kosher, could the observable universe boundary be evidence for the alien zoo hypothesis? I mean, it would be a weird fluke that the aliens have decided to erect a sphere around the Earth that is 46.5 billion light years in radius, and that every year they expand this sphere by an equivalent amount of the expansion of the universe to make sure that no part of the edge of the outside of the observable universe is possible. But it doesn't matter because we can't see earlier than 13.8 billion light years ago, or 13.8 billion years ago. And so it would be very heliocentric for us to think that we are the center of the alien zoo hypothesis. Now, that said, of all of the possible explanations for the Fermi paradox, I personally find the alien zoo hypothesis the most plausible, or the second most plausible after we're alone. It's the one that would explain everything, that we live in a simulation, or we live in a galactic zoo, and that someone is attempting to manage our perception of what we see. If they're sufficiently advanced technology, they can decide what we can see from the surface of the Earth. They can surround the Earth in something that changes our perception of what's out there in the real universe. And only by breaking beyond the boundaries of this would we actually see what's truly out there. I don't believe it. I think we're alone in the universe, and that's why we don't see any aliens. But of all of the possible explanations, yeah, I think that's the one that answers all of the questions. Maggers 12. Fraser, this one has always bothered me. Oh, here we go. Confused me now. My grandson has asked me, and I'm unable to give him a satisfactory answer. How can the universe be infinite if it was created at the Big Bang? So this is one of the perennial questions that we get here on the channel, and I feel like I need to answer this question every 3 episodes or so. But good question, grandson. Here comes your answer. So the first thing is to understand that when we talk about the universe, we're talking mostly about the observable universe. That when we look in one direction, we are able to see out to 46.5 billion light years in one direction. We look the other way, we see 46.5 billion light years. That is because the universe has been expanding, and the amount of time that has elapsed is the age of the universe, 13.8 billion years. And that if you sort of run the tape backwards, then you're going to see the size of the observable universe come down when it's just based on the amount of time that light has been able to get across. And if you roll all the way back, then about 380,000 years after the Big Bang, the entire universe was kind of like the entire observable universe. Like, I gotta be really clear about this. The entire observable universe was like the surface of a star, and it was opaque. And then if you keep rolling the clock back, then there was a time when the entire observable universe, this is about the first, say, 12 minutes after the Big Bang, the entire universe was like the interior of a star, very hot. Fusion was happening, turning hydrogen into helium. And then, theoretically, the entire observable universe, say it with me again, was the size of a volleyball or the size of a pea. We don't really know. Or maybe it was almost infinitely small. But that was just the observable universe. And so outside of the observable universe was more universe, the actual universe. And we don't know how big that was. It might be that the actual universe was infinite, that we have our observable universe that is compressed down to the size of a volleyball, and then right next door is another one, and then right next door is another one. But, obviously they're not, they're not spheres. There's an infinite amount of universe. It goes off in all directions. And then we got this lowering of density, we call it expansion, but really it's just that the universe was becoming less dense over time. But it could very well be that over the cosmic horizon, the places that we can't see because the light hasn't reached us yet, there is just more universe. So the universe, if the universe was infinite, or if the universe is infinite today, it was probably infinite at the time of the Big Bang. That we're only seeing one tiny little portion of the true size. And we know that the universe that we can see is like less than 1/1000th of the volume of the actual universe. Like we can measure the minimum volume of the real universe, and it is going to be about 1,000 times. Like the bare minimum is that it's 1,000 times bigger than the universe that we can see. So you imagine, take the universe that we have, and then imagine 1,000 more packed in a volume, right? That's the bare minimum, but also maybe infinite. It goes on forever in all directions. Did that help? I need your grandson to, I don't know if he's watching you live with this, but I need him to go, okay, I got it. Or, Maggers, have you got it? And now you can pass this along to the grandson. And so just remember to be really clear about that idea of the observable universe. And the sort of the way I always describe it is like it's a grid. You imagine there's like a grid today that's getting bigger, where the gaps between parts of the grid are getting farther apart, and then you can just kind of run backwards, and the parts are going to be getting closer and closer together. So, but yeah, it's this. The classic question is, well, if the universe started as a singularity, how could we say that it's infinite today? And it's that the universe wasn't a singularity. The observable universe could have been a singularity, but there would still have been more universe outside of the observable universe. Okay, you know what? We've reached the end of our time, and so now I am contractually obligated to let you go out into the world and enjoy, stretch your legs, go reconnect with your loved ones, watch the television shows and anime and video games that you have been set aside to share with me for this very special episode of The Question Show. Thank you, as always, to the incredible heroes who really make this show possible, and that's the moderators. So Zapfan, John Suffill, Series K. Lee, and the others who are here. The show is made so much better by having their company. Thanks in advance to Chad and Anton, who have to deal with this nonsense and turn it into some kind of coherent, cohesive episode. Good luck, guys. I don't want your job. All right. We will see all of you next week. Or sooner. Whoa, 666 concurrent viewers. How cool is that? Bye.